So today we'll discuss about flow meters, flow measurements. And first important thing about flow measurement as far as instrumentation and industrial instrumentation is that why do we need to measure flow? Because we are having different types of processes that are happening in industry. For instance, you have to mix different quantities of liquids, say for instance in a food processing factory. I mean a jam making setup or a beer manufacturing brewery. That's what. All these places you need to have quantities measured. See, even in a chemical plant you have to measure the quantity. So the liquids, they may be viscous liquids, they may be less viscous liquids, there may be hot liquids. Then when you talk about flow, it means fluid flow. That means it involves gas, steam, and also liquids. Okay. So all these are part of measurement. And today we'll discuss about say one particular type of flow meter, which is called as an orifice plate. And as a background to this, we'll see what is being as a background to this. We'll have a discussion about what are the basic principles involved in flow. Okay. You can hear me, no? Yes? Someone, can you respond? Hello? Yeah, okay, fine. So I'll provide the recording of the session also, so that someone loses out in between, they can make use of it. So I'm recording it also. So you can ask doubts or anything, you can step in at proper times. I'll respond. Okay, you have to respond audibly. So we are aware of this, the laminar flow and turbulent flow. So for a lot of purposes, we are happy with the laminar flow because the particles are all in a stream. They are in a stream. That is, a particle. If you trace a particle, you can trace a particle within a fluid. You can observe its path along the fluid. The fluid flow will be in parallel layers. There won't be mixing between these layers. Compared to that, turbulent flows there where the different streams they mix. Mixing may be partial or it may be very full. So you can what image that comes in your mind is the reverse in the upstreams. Just like whatever you can think of in the Himalayan region, those areas, Rishikesh and all those places. One particular value which you would have come across in your physics classes is about Reynolds number. Okay. And this is a rule of the thumb to characterize between laminar flow and turbulent flow. And here we have the specific density, the characteristic length. So characteristic length has to do if you have a circular excuse me, I'll just take a moment. So this great person, Daniel Bernoulli, is the key person in this whole business, at least to some extent, the initial parts of the discussion which we will discuss today. You are aware about this Bernoulli's principles and the Bernoulli's equation. and we are using it in different contexts. Okay, you are using it in explain the how aircraft lift is generated. Okay, aircraft flies. Then you are explaining in terms, say, the Bernoulli's principle has quite a lot of extended applications also, where you can measure, say, if you know the pressure head and all those parameters, you are going to measure what will be the rate at which a tank empties. All those things can be measured. So the equation in this format is basically it is a statement of the law of conservation of energy. If you have fluid flowing, fluid means a liquid or a gas flowing through between 2 points, say P1 and P2, it should obey the law of conservation of energy. And this Bernoulli's equation has 3 parameters. One is the pressure head, that is the applied pressure. The static pressure, you can say, that is the pressure energy. Then you have the kinetic energy, which because of the velocity of the fluid, V1 and V2 at these 2 places. And then you have the potential energy. In this particular example, this is at the same level. This tube height is h1 equals h2. So, but you may have 2 different levels. Okay, for instance, the picture that comes in your mind is of a penstock pipes of a dam, okay, or the water flowing out of a water tank. So these are 2 levels. There is a potential energy. So when the fluid flows through this particular section, say it is a constriction is there is a constriction here. Ideally we expect its pressure to not ideally, in a common thought processes we say that the pressure would P2 will be higher. But what Bernoulli's principle states that when the energy, the kinetic energy, the velocity of this, when it goes through this constriction, the velocity, fluid velocity V2 will be greater than V1, and consequently there will be reduction in the pressure. Consequently there will be reduction in the pressure because A2 is less than A1. So this is the key thing there. Actually there is a transformation of energy from one form to the other, static to dynamic. That means the static pressure energy is converted to kinetic energy. So that's why V2 increases. So it balances between these 2 points. So this particular figure is from this particular website. In fact, a person from the 18th century is still having a lot of influence on the way we understand the fundamentals of physics. That's really marvelous. Okay, so moving on, the fluid velocity increase is accompanied by a decrease in the pressure. Okay, coming to flow meters. Flow meters you can divide into 2 groups. One is what you call as one type of meters, they measure quantity. That's called as a positive displacement type of flow meters. The other measures rate of flow, or you call them as inferential type of flow meters. So and in fact all fluid meters consist of 2 parts. One is what we call as a primary element, and primary element will be in contact with the fluid, and maybe it might be a wheel, rotating wheel, a vane, something like that, and that results this interaction with or a paddle wheel, all those things that will result in some motion to the primary element. Karang, or chakra, or vane, all those things could be there. So and this interaction between the fluid and the primary element is conveyed to a secondary element, which will convert into some measurable value, into a volume, weight, or rate of flow. So, and this are the 2 distinct parts of a any type of flow meter. And there are some common types of flow meters which fall into these two categories, and we'll be studying quite a few of them. In fact, this particular module, the module 3, is fully dedicated for flow meters, and most of them are mechanical type of flow meters. So, and we'll apply some electronic principles that's there. So we don't cover quite a few things. How does the seepage water in a dam, how is the seepage water in the dam measured, all those things, how much water leaks out of, for instance, the Mullaperiyar Dam. There are specific types of devices, very crude but very useful type of measurement devices are there, something like a V-groove structure, which is placed in the path where the water flows, and you can measure. That's how they record. They are not going to use very complex instrumentation. They have electronic ways to do that, but really very simple mechanical structures are used for this. So we'll today take up this Orifice plates. Orifice plate, it's an inferential type of flow meter, and the Venturi meter and flow nozzles are direct extension. In fact, the Orifice plate, Venturi, and flow nozzles, you would have even pitot tubes. They are used in aircrafts to measure the air speed. Aircraft in the side, usually near the front part, nose cone part, there will be this pitot tubes, something which projects out. All these three, in fact the first three of them are directly based on the Bernoulli's principle. Okay, then in the other category you have different types of movements in the parts. That's what the positive displacement meters. Reciprocating, rotating, nutating disc, sliding and rotating vanes, a geared and lobed impeller. So you'll have to draw some figures. In fact, you require to draw neat figures, not very artistic, but still you'll have to illustrate the concepts. Okay. വരച്ചാലേ എഴുതാൻ പറ്റുള്ളൂ പേപ്പർ ഈ ഒരു സെക്ഷൻ. So Orifice plate is a simple flow measurement device. Basically it will be a metal disc which has some hole, and it will be fixed onto this is a cut section of a pipe showing an Orifice plate which is put there. Orifice plate will be having hole. It might be a single hole as shown here, or it may be multiple holes. So different shapes and sizes of this are there. This will be the upstream pressure, this will be downstream pressure. So if you, for simplicity's sake, we will take the case of a Orifice plate which has a single hole. So if you apply the principles, Bernoulli's principle, you will know that your pressure head on this end will be reduced, the velocity will be increased. So if you measure the differential pressure across these two, that's what, and correlate it to the flow. In fact, a square relationship exists. Square relationship exists between the differential pressure, that is a pressure between these 2 points, that is P1 and P2, and the flow. You will be able to make a measurement. That's a basic idea of Orifice plate for flow measurement devices. Can you hear me, people? You can see the slides also. Okay? Hello? So this is the much more detailed description of the Orifice plate. So your pressure head P1 is on this side and P2, and the direction of flow is along this direction from left to right, and you have put a differential pressure measurement device. That means we mentioned that is gauge pressure, absolute pressure, differential pressures. Okay, so differential pressures. So this is a differential pressure measurement device. This particular topic I didn't take in the module. Okay, last module I just skipped over to this wheel. That's the last topic in the second module. That's left out for exam as well. In the series exam. We'll discuss it at some point. The concept is clear. You have to a differential pressure measured. That's a basic across two heads. That's it. So here you see that this is an orifice plate. This is a single orifice plate, and it has something written also. You call this as a paddle. This long structure, and there'll be some written. So things on this, you'll be fitting it in this flange. This is a flange. You call this section as a flange. This couple of mechanical terms you would have to remember. Flange, okay, and you will just put it there. So the one problem is that if you want to service the orifice plate, you will have to take down this section, cut down the flow, and then you do that. That's the drawback of this orifice plate. Okay, repair othedellam buddhimuttanu. But there are other alternatives also, which can do without even shutting down the section. So coming to this point where it contracts, the flow contracts. That's what you call it as vena contracta. That means it contracts, and it's the area of minimum pressure. You can say that P2, and it depends on the precise location of this. Depends on various parameters. That is, which varies with the flow rate, the beta ratio, and the inside diameter to the bore diameter, the diameter of the orifice plate hole. All those, it depends on these parameters. Okay, so again, so the vena contracta is a point where the flow velocity will be the maximum, in fact. Now, a problem with the orifice plate is that your pressure P2, that is pressure after the orifice plate, will be less than the pressure upstream. You'll lose some pressure to go through this pipe. So the process pressure will decrease. That's also a logical thing. There is a particular structure, graph which illustrates how this happens. Say this is your pressure upstream, this is P1, and this is your orifice plate section. This is a pipe, okay? This is a pipe, and this is a manometer which is put at these 2 points. So this here, the manometer is up here, and so here again. You can't say it's a manometer as such, it's just a tube there, shows. So it's a graph slots. So your pressure head is decreasing up to the vena contracta, and then it gradually increases. But it will be never matching up to P1. This is a permanent pressure loss, P1 minus P3. There is a permanent pressure loss. That's also really logical. So that is in fact a drawback of this orifice plate. That's a drawback of this orifice plate. You will have to manage up various parameters to make sure that if you are inserting an orifice plate, you are ready to sacrifice some sort of pressure loss. But orifice plates are one of the most widely used flow measurement devices in industry. So, so velocity increases, then the pressure will decrease. So this is what is mentioned. Okay. And also pressure. The other thing is also there. When your flow increases, the pressure drop also increases. It's there. And when there is no flow, there is no differential pressure. If it is stagnant, there is no differential pressure. That's also fact. So that means that brings us to the derivation also. Before that, I would like to mention that this with the simple principles you are going to measure the flow and how we correlate it with the pressure head. That's what the idea to measuring the flow. We'll come to that. Before that, we need to go into some of this maths involved in this. So this is from Professor Sahu's lectures, IIT Hyderabad. Okay, this so he is illustrating it very well. So I just borrowed the slides sections from here, and it's self-explanatory. You are applying the Bernoulli's equation at these two sections, that is P1 and the vena contracta, and then you are balancing it, and this is the, what do you say, the potential component, potential energy component, Z1 and Z2. We assume them at S2 at the same level. Height difference is not there. Z1 equals Z2. That will be the ideal case. So, and there is a head. Differential pressure head is balanced to the velocity. So, and coming to this, if you assume A0 as the area of the orifice, and there is a parameter which is defined as coefficient of contraction, which is A2 by A0. A2 is the section here. Okay, and fine. So A2 is a section here, the vena contracta, and then you applying this continuity equation. Continuity equation is basically a mass flow statement. That is the velocity multiplied by the area. That means a mass flow will be balanced. That's there. Fluid is not going anywhere else. It's so you are not going to apply this Bernoulli's principle to turbulent flows. Okay, Bernoulli's principle works very well for laminar flows. You are not going to explain it for turbulent flows. Turbulent flows, the Bernoulli's principle fails. It falls short of that. Short of explaining things for turbulent flows. And then from this you can explain what is a flow. The flow Q, and you're balancing these two expressions and making the substitutions for V2 is substituted here, and you will define a parameter which is called the coefficient of discharge, CD. Usually the CD value is given along with the data sheet. If you have a orifice plate which is for a particular type of fluid, this will be mentioned, the coefficient of discharge. Coefficient of discharge, and you are substituting it, and finally you end up with the expression for this flow. So all basically what it states is it depends on the cross-sectional areas of A1 and A2. That's what, and the pressure head and acceleration due to gravity. A simple relation is there between these parameters. So it's just a matter of plugging in these values and getting you have these thing coefficient of discharge already from manufacturer's data. A1, A2 is also mentioned. It's just a pressure head that's we need to calculate. That's also the simple thing. So what way we going to measure is based on the differential pressure. Differential pressure, as we saw here, say differential pressures P1 and P2, and it is related. This is a simplified statement of a simplified statement of your Bernoulli's equation. Okay, applying the continuity expression, equation of continuity along with Bernoulli's principle, you will end up with this expression. You get a square relationship between the flow and the differential pressure. So square root of Q is square root of K, K into delta P. Delta P is the differential pressure between these 2 points. So your other factors, you keep it as constant. All those A1, A2, all those things are going to be constant. So you end up with an expression like this. So this is the basic principle in orifice plate. And then the advantages, these are the advantages as we mentioned. So the simple construction, it can be just no other complication is just put a choose a plate of a particular diameter, put there, you know the parameters, make a differential pressure measurement, and that's it. disadvantage is the pressure loss, and you need to obtain a laminar condition, laminar flow here, and it's going to be inaccurate to some extent, 2% to 5% inaccurate. It should be full. The pipeline should be full. There are viscosity is going to affect your measurement. You can imagine using an orifice plate to measure this what do you say, a thick fluid, maybe a thick fluid flowing through this thing. Quite a few fluid particles will be suspended always near the orifice plate, and that's going to reduce the bore diameter. So such things are there. There are other alternatives also to prevent the sedimentation or clogging of this orifice plate. So you have different geometries for the orifice plate to use it for different applications. So you have concentric type, eccentric type, segment orifice plate, or quadrant edge orifice plate. We'll just see the various types. For each of them, there are very ready-made expressions relating the various geometry and to the flow. That all those I don't think we need to be really stressing on, because mechanical engineers should be taking care of this, but you need to be aware such things exist. So even though the sections appear similar, this is, if you see this is a square edge eccentric, so it's off center, and there is the hole is towards the bottom. So this is a paddle which is used. You'll have all those writings. തിരിച്ചു വെച്ചു കഴിഞ്ഞ പ്രശ്നം. Say if you will have to really note the direction to which it is to be oriented. You see from the side view, you see that even though the top view shows it as a circular section, but this is in fact having variable diameter. So orientation will be mentioned, which is the inside, upstream side and downstream side, that will be clearly written on this paddle. തിരിച്ചു വെച്ചു കഴിഞ്ഞാൽ, if you just put it in the other way around, that's going to be not the right way to do that. Okay, again you have segmented square segmented sections. Then with the drain holes there are something which is called vent hole and drain hole. So this is, if the gases are stuck there, they will be vented through this vent, and if there are some clogging particles suspended, they will be leaking out through this section. That's for that purposes you have vent hole and drain hole. For gases you have vent hole, and drain hole you have for fluids. Okay, so that this as